Okay, so we covered homogeneous. So second order homogeneous was harder than first order because you couldn't just read the left-hand side and just say CE to the whatever negative of whatever t. You had to you build the characteristic equation, which was something like r squared. This one was this quadratic thing, which we showed by saying that if you plugged in a solution form of, the same solution form we saw for first order equation, CE to the RT, turns out that that is going to be a good solution form because the derivative of an exponential is itself. And so you'll have a bunch of exponential terms on the left here that you're just hoping to find C and R that would make it all vanish. If you do that, you'll end up getting that if you're interested in non-zero solutions, so when C is not equal to 0, the R has to satisfy this, and there's 3 cases: distinct real roots, repeated roots, and then complex roots. So it's a little more work than just reading off the left-hand side. You have to do solve a quadratic equation. And now we're looking at a right-hand side that's not 0. So this is a non-homogeneous differential equation. But again, this turned out to not really be much different because you can imagine that if you're trying to get a polynomial on the right-hand side, on the left-hand, you want to have a polynomial on the right-hand side, and you want to match, have a solution that will make the left-hand side match that. You would expect like another polynomial to be the solution form. And it's like basically the same thing that you would have done if it was a first order equation. You just build it off of the same degree polynomial. So if this is a first degree polynomial, you'll basically have a first degree. You could go higher degree than that, but it's unnecessary because you would get like the coefficient of the higher degree term to be 0 anyways at the end. So might as well not have included that to begin with. The constant is not going to cut it for this because if you had plugged in a constant, then all you have is constant terms on the left when you need a t term to show up. So if you just do this one, you'll just say, okay, the same thing that you done before, it's just going to be like your xp is equal to your polynomial here is going to be your a naught plus a1t. And you're just going to plug this in just like we've done before. And you'll just get that. You have to take you'll have to take multiple derivatives of this thing. So if you took the derivative of this, you'll get a1. And if you took the derivative of that, given that a1 is a constant, the second derivative term is 0. So that's x double prime. Minus 3, the derivative term is just a1. And then it'll be plus 2 times this whole solution. So it's going to be a naught plus a1t. Same thing that we've seen before. It's just that now you have an x double prime term when you plug it in. And then you're just going to rearrange so that you'll get all your terms to, sort of be all the t terms. So you'll have your 2a1t is going to be your only t term. And then you have your 2a naught, and then a minus 3a1. And then that has to equal your left-hand side, which is this. And you'll see that there are sort of, this has to match with this, and then you have this has to match with this 5. And so you'll get that your 2a1 has to match. So if you know that 2a1 has to equal 2t, that means you know immediately that a1 has to equal 1. So that gives you one of the coefficients. And then you'll get to use that when you use the second condition, which is like 2a naught minus a1 has to equal 5. And, of course, you can just plug in this previous, the one that we got from this part into this a1. And then so you'll get that you have 2a naught minus 1 equals 5. And so you, sorry, there's a 3. Let's see here. So this has the 3 right here. So this is a 3. And then this will make it minus 3. And so you'll add 3, that'll make it 8. And then you're dividing by 2, so that means that you'll get a naught is equal to 4. And That's it. So it's not different from, what you've seen before with first order equations. This just gives you that x of p is equal to a naught is 4 plus a1 is 1. So it would be 4 plus t, because this is a1 right here. And the particular solution is done. Nothing new. The solution form is also what we expected from first order equations. So I'll just have a little bit of space here to do the homogeneous, because unfortunately I can't just read off. I have to actually build a characteristic. So it's going to be r squared minus 3r plus 2 is equal to 0. And this factors to r1 times r minus 2 is equal to 0. So therefore, your r is equal to 1 and 2. So that gives us that our homogeneous solution is there's going to be two of them, c1 e to the t, because there's a r that's 1, plus c2 e to the 2t. And so you have your homogeneous solution, and then you're left with just adding those together will give you the full general solution. So your general solution, x of t, will be built off of your particular solution, which is this, plus your homogeneous solution, which is this. And so here's your particular solution. So the only thing that's a little bit of more work is that when you plug it in, there's a x double prime that you do. And then there is some more extra work for trying to come up with a homogeneous solution. This is x of h. So that's your full solution that's built off of your particular and your homogeneous. And you have two arbitrary constants, C1 and C2. That's always going to be the case when you have second order equations. Yes. So these you just remember with the first order case, you end up plugging it in and you get just r plus 4. It also makes sense because every time you see a derivative term, that's r, and every time you see a constant term, that's 4. And then this became r is equal to negative 4. But the solution form we plugged in was just r here. And the same we did with the second order equation. So this is consistent with what we said. If we got, like, in the past, this was the first example we did, r squared minus r minus 2. We got r is 2, r is negative 1, and those just go directly in there. So it's yeah, be careful. This goes directly. There's no extra minus that goes in because we just proposed that it's e to the rt at the very beginning when we built the characteristic equation, not e to the negative rt. And we could have done the same thing with first order equations. We said c e to the rt, but it shows up that in this case, you get r plus 4 and r is equal to negative 4, just to show that it's consistent with what we had been doing in the past. So that one's that. And then let's see here. So we have the solution for this. Now, this is a first degree polynomial. It has a first degree term and then a constant term. This one only has a first degree term, but even if it has only a first degree term, it's still a degree 1 polynomial. So you would have to build the solution as a general first degree polynomial. Like you need, even though this looks like it only has a t, you need both a naught and a1 in your solution. And so you'll plug this in. It's going to still be the same idea on the, so you take the second derivative, you take the first derivative, it's a1. If you take the second derivative, it's 0 because the derivative of a1 is 0. And then you're just plugging in the x prime is going to be a1 is equal to t. But this has an issue because if you solve for a1, first of all, a naught disappeared. So it's like, how can I even solve for a naught, And it also gives you that a1 is equal to not a constant here, right? Because t is not a constant. So this is an issue because we assumed that a naught and a1 were both constants in the process of plugging it in. We would have not gotten 0 here or a1 here if we didn't assume that a naught and a1 were constants. But then we're sort of contradicting ourselves and saying that, and we saw this in the past. And so this is not going to give you something that is going to work. In fact, if you try to plug it in, let's say a1 is t. If you said a1 is t, then let's see what that'll give us. You'll say, well, we don't know what a naught is, so you might think that you could just say whatever you want for a naught, and then a1 is equal to t will give us t squared here. See what happens if we actually check this. So if we check and plug this in, then if you plug it in, then you'll get, I'll just do it right here and say, okay, if you plug it in, then you're just going to take the second derivative. So if you take the derivative, it's going to be 2t. And then if you took the derivative of that, it's going to be 2. Plus the x prime is going to mean that I don't take the prime. If I take the derivative of a naught, it goes away. So it's be 2t is equal to t. And that's definitely not true. This is false. So you don't have the same thing on the left and the right. So this actually is not the correct solution form for this. So this is something new. You know, from the first order case, we saw that if you have a first degree polynomial here, then you could just write the general first degree polynomial and you had no issues. But this is a second order problem that has this kind of thing happens more often with the second order, where you have to do an additional modification to your initial solution form. And you already knew that there's some kind of thing, the fishy thing going on, because you're assuming a naught and a1s are constants in the process of plugging it in, but then you later get a contradiction and say a1 is not a constant. We've seen this in the past, and every single time we've seen it in the past, if you try to use this non-constant a1 in your solution and try to plug it in, you'll get a false statement. And so this means that we have to do something additional to this. But I don't want to go into that today, so we'll do that next time. And so I will stop here and then try to give you guys the